So hi everyone, in the previous video, I have discussed about address binding. So when we need to execute a certain program, we need to load it into the memory. So as you can see here, it is loaded from 5,000 until let's say 5,004, assuming it is a small na program. Okay, so each of the instruction has a certain physical address, and that's what the CPU uses to know which instruction to fetch. And today, I am going to discuss about the problems with the physical addressing and how we can make use of virtual memories. Okay, so let us start with a scenario. Let's say that you are running the same code, but then we have limited the memory at the moment due to several applications running in your system. So this is a problem of limited the memory capacity. So with a limited na memory capacity, it becomes challenging to support larger programs or handle memory-intensive tasks. So we can see an example here. So assuming that you have a very large program, and then we have a limited na memory. Okay, so as you can see here, each na line is being mapped to a certain physical na address. But then when we got to the rest of the lines, there are no more space in our memory. So where can we possibly store this? And if we run this program, it will crash because these lines are not mapped to any address. Okay, and so that is the problem of capacity. And there is also a problem of memory management. And we have several na processes here. Let's say you are running Android Studio, you are playing playing a game, and then there are also some system processes. So how actually is it being managed? Since this is a simplistic na view, but then in reality, let's say in just the Android Studio, there are several threads running, several processes running in one application. So how are we going to manage the memory such that they do not overlap each other? Um, they do not override each other's data and instructions. Okay. So also, if let's say we have this Android Studio and it has been allocated this memory, and then after a while Genshin Impact is going to um s- to take its turn, and it will be swapped with the Android Studio. So every time that we do some swapping, there is some context na switches. And note that every process that we have contains a stack, a heap, a data, code, registers, etc. So every time we do context switch, all of this data, all of this data in the memory that is loaded in the memory must also be context switched. Okay, so can you imagine how expensive that is? So yeah, it is very expensive. And then another is that the memory protection. So in physical na addressing, it lacks memory protection mechanism. So in a system with just the physical na addresses, a program can access any memory location, potentially causing unauthorized access or modification of a critical na system data. So that's why memory protection is very crucial, and that cannot be provided by physical addressing. Okay, and also the problem of sharing. Physical na addressing does not provide a straightforward na mechanism for memory sharing among multiple na processes. So for example, if we have these two running applications with plenty of processes and threads within this each na application, how can we share memories? So sharing memory allows processes to efficiently communicate and exchange data also. So without a mechanism for proper memory sharing, so the interprocess na communication would also be more complex and less efficient. Okay, so one solution would be the use of a virtual memory. So a virtual memory is a memory management technique that allows the operating system to use a combination of physical memory, which is the main memory that we have, the RAM, as well as the as a secondary storage like the hard disk that we have or the SSD. So in order for us to provide a larger contiguous address space to programs. So let us see an example. So problem one that it solves is the capacity. So earlier, we have shown you an example wherein the program might crash since we have a limited na capacity. But in this case, we are incorporating a map that in which its job is to map the physical na ay, in which it maps this program into some physical na address. So we have the rest of the lines that are not loaded into the memory at the moment. So in this case, what we are using here is a virtual na memory. So as I mentioned earlier, when we use a virtual memory, we also use a combination of the main memory as well as a secondary memory like the SSD or a hard disk. So a virtual memory takes some space from the SSD or hard disk since we know that our secondary memories have much bigger na space compared to your main memory. 'Di ba? Your main memory can only have 8 gig or 4 gig, but your hard disk could be 1 terabyte or more if you have a bigger na space, diba? So what we do here is instead of forcing all this the rest of the code to be stored in the or loaded into the main memory, we map it into a virtual memory instead, wherein this virtual memory is stored in the secondary na memory. Okay? Yeah. So, and then, for example, what happens here is if we have, let's say, the oldest na data that was loaded in the main memory, we can transfer it in the virtual memory, and then this line 6 can be additional na line may then be stored into the main memory. Okay? So that's it. So that's just the idea. So it makes use of a virtual na memory which uses a space from the secondary memory. So with this, it gives us the illusion of a larger contiguous address space to programs. So it allows programs to operate as if we have more memory than what is physically available. Okay? So what else? So we have this general na form of virtual na memory. So we have a program that is mapped into its virtual na address space. And we have a memory management unit, which is a hardware component within the computer CPU. Within a computer CPU that handles the translation of virtual addresses to physical na addresses. Okay, so what the MMU does is it performs the necessary na address na translation by using some tables to store mappings between the virtual address and the physical na address. Okay, so in this case, the physical addresses then are invisible to programs. So the programs are only it's only the virtual addresses that are visible to programs, right? So as you have remembered in the memory hierarchy, this shows how the memory hierarchy can provide a solution. Okay, so by incorporating secondary storage such as hard drives or solid state drives, computer system can store vast amounts of data beyond the limitations of the main memory. Okay, so if you have watched my video on on memory hierarchy, you would understand what I mean. Okay, so it also solves the problem of protection and memory management. So in here, what we have is each of our programs. We have multiple programs now. And our question earlier was, we go back here, how are we going to manage having multiple processes, having multiple applications? How do we store that in the memory? So in this case, what we have is we have a separate na map for each na process. Okay. And then this virtual addresses takes some contiguous na memory from the physical na address. And then we also have another na program which is composed of its own virtual addresses, which is mapped to some physical na address. So we know that if this memory is allocated if this main memory is allocated to this certain program, so program 1 cannot take that, okay? Cannot take that. So each process has their own virtual na map. So it is much easier to manage then kasi naka-group siya. So lahat ng mga processes na under sa program na to, or lahat ng threads na under sa program na to, naka-contiguous na memory block siya sa physical na address. And so hindi siya kalat-kalat kumbaga. So it's not difficult to manage information, and it's also not difficult for different processes and threads to communicate with one another because as you can see, contiguous siya. Right? And also, this certain na memory location or allocated na memory for this program will not interfere with the memory that is allotted for another program. Okay? Yeah. So it lessens the some error, and it also solves efficiency. And another na advantage of this is you can subdivide. You can subdivide a certain program. So for example, this program 2 has been allocated a memory here. So this space is not enough for program 1. So what we can do is we split the program into, let's say, into 2, and the first half may be stored in this location and the rest will be stored in the other na chunks. So note that the size of the physical address here is the same with the size in the virtual na address. Okay. So yeah, in the next na video, we are going to discuss about paging and segmentation. So that's all for this topic.